The first thing I would like to do is to explain special relativity using little pictures that anybody can understand. It's the same mathematics, but also I'm using pictures to help explain what we're doing. We have a little space-time diagram here where the flat line is XYZ space, and we have two particles moving forward through time. One is stationary at v equals 0, the other is moving to the right rapidly at v much greater than 0. Each of these particles counts time. Now, the first stationary particle over here counts length time t in going from the bottom to the next dot. The other particle counts time t prime, which is longer. That's what they call time dilation. So how much slower is it for one particle than the other? And if you drew the lines differently, you could see the effect would be a reciprocal. Well, what we can do here, we define a little angle theta, which is an angle through time between time and space. And the key formula is sine theta equals v over c. By simple trigonometry, we get cos squared theta equals 1 minus sine squared theta, 1 minus v squared over c squared. Therefore, cos theta equals t of t prime is the square root of 1 minus v squared over c squared. And you can see that's just a cosine to define time dilation. So using this simple method, we can understand special relativity in terms of pictures. I've done this for every possible thing in special relativity, and it works all the time. It's very good for students if you want to teach them better, because then they'll understand what they're doing. Now that we understand special relativity in terms of pictures, we're going to show deBroglie waves in terms of pictures. I'm not sure how to pronounce his name, which is French. We'll just say deBroglie for now. We have a similar space-time diagram as shown here, just like before. X, Y, Z space in 3D is a horizontal line. We have two different particles moving through time. One is stationary at v equals 0. The other is moving to the right very rapidly at v greater than 0. And now we're counting, instead of time, we're counting a frequency through time, the fourth coordinate, which I call F4. The stationary particle counts F4 going up that way. The moving particle counts F4 prime going up that way. And F4 prime is bigger than F4 by an amount given by this angle theta, which is defined as before. Now, what are deBroglie waves? deBroglie waves are the difference between F4 prime and F4, F4 prime minus F4. So let's evaluate them mathematically to see how that works. We define a quantity delta, which is the difference in frequency, F4 prime minus F4, and that's clearly, by geometry, F4 times 1 over cos theta minus 1. Now, if we substitute in, that's just F4 times 1 over the square root of 1 minus v squared over c squared minus 1. Simple substitution. And for small v over c, delta, which is the difference in frequency, is the deBroglie frequency, and it's approximately F4 times v squared over 2c squared for small v over c, as is well known. So now we've defined not only things like time dilation in terms of this little space-time diagram, but we've also defined the deBroglie waves as the extra frequency that goes into our space when a particle is moving. So it's just F4 prime minus F4, and it's this little quality here, delta. Because when there's no velocity, there's no deBroglie wave, so it's all the extra frequency. Let's analyze that a little further now to get an interesting result. Next, after some simple algebraic manipulation, we learn that h times f4, which is the frequency of an electron at rest moving through time, equals 2 times mc squared for small v over c as an approximation. That's a very important result, which is unexpected, and we'll explain why now. The reason why this result is unexpected is because the electron at rest shows twice the frequency through time as for conversion of its mass to light by the formula hf equals 1 times mc squared. Now we've got hf equals 2 times mc squared, so the frequency is twice as high as expected. Finally, because the frequency of an electron through time is twice that expected, we see g equals 2 for the intrinsic spin magnetic moment of an electron. In other words, if you put an electron in a magnetic field, it makes induced currents which are twice as much as expected because the frequency of those motions are twice as much. H4 equals 2 times mc squared and g equals 2. Thus we have a direct structural relationship between these two values, and that's not something which was known in physics before.